So simplifying radical expressions, and we're also going to include multiplying and dividing radical expressions. First off, whoa, okay. So the square root of a number, b, right, is a solution to the equation x squared equals b, right? But every positive number b has two square roots, square root of negative b, or positive b, and square root of negative b, right? And the way that you can kind of think about that is, think about like square root of 16. It's 4 or negative 4. Why? Because 4 squared is 16, but also negative 4 squared is 16. So whenever we're doing the square roots, we kind of have to take that idea in mind. So for example, square root of 25 is 5, right? But you also have to think about the negative square root of 25, which is negative 5, okay? Because negative 5 squared is 25, and 5 squared is also 25, okay? So you have to think about both plus and minus. When we talk about the positive square root, we always refer to that as the principal square root. Okay. So a cube root. Okay. So square root. That's something that you guys should have used before. But a cube root now is a little bit different. Maybe you have or haven't seen this. It's essentially the same idea, except for, right? If you think about a square root, it's what number times itself one time, or twice technically, I guess. Yeah, number times itself will equal this number. When you're doing cube root, you're thinking about, all right, what number times itself 3 times will give me this number, okay? So for example number 1, the cube root of 27, what number times itself 3 times will give me 27? Yeah, 3. It'll be 3. And, oh, sorry. Okay. Come on. So it's 3, all right? But the thing that you but the thing with cube roots or with odd number roots, right, is a negative times a negative times a negative is what? It's a negative. So unlike square roots where I can't take the square root of a negative number, else it'll be an imaginary number, I can take the square root or the cube root or an odd root of negative values. Okay, so for example, on number 2, cube root of negative 8 would be what? Negative what? Negative 2. Okay, right? Because it's negative 2 times negative 2 times negative 2. What about the third root of 10 to the 6th power? What do we think this will be? Any ideas? It's going to be the same thing as 10 squared. Why? Because if you think about it, you're breaking up 10 to the 6, right? If you break up 10 to the 6th, it's the same thing as 10 squared times 10 squared. And so you basically just found the 3 numbers that multiply itself to each other to get that square root. Okay? To get that cube. All right, so now I've got a little bit of practice for you guys. I want you to try and find these solutions. Okay? I'm going to give you guys about 2 minutes to try and find these values. Okay? You guys about 2 minutes to try and find these values on your own. Oh my gosh! Can people on Zoom not see this? Love it. Love it. I love it. Chock full of errors today. Chock full of them. Maybe Mr. Keeper should just retire for the day. Call it good. Just go home. If you have the slides open, you should probably already know what the answers to these are. All right, so when we're thinking about, for example, on number 4, right, we're thinking about, okay, we're looking at the 4th root of 81. So what we're looking for in this case is we're looking for a number that if I multiply it to itself 4 times will give me 81. Kyla? Got 3. Right, perfect. Because if I multiply 3 to itself 4 times, it's because 3 to the 4th is 81. And that's kind of, oh shoot, I didn't mean to do that. But the 5th root of 32 is going to be 2. Because if I multiply 2 to itself 5 times, right, I get 32. What about the 3rd root of negative 1 over 27? Yeah. But it would be what? 1 over negative 3 or negative 1 over 3. And we'll go over why this happens in a second because we're going to review some of our rules. And then for number 7, 1 over the 3rd root of 64. Yeah. 1 over what? Yeah. It's 1 over 4. Because 3rd root of 64 is 4. Okay, so pretty simple stuff. Hopefully. Okay. So now if we're trying to find the real roots of each of these equations. So if we have x squared is equal to 81, right? The idea is we're trying to isolate x. So what we can do is we can take the square root of both sides. And we've done this before when we're trying to solve. Remember when we did the square root method, right? That's why it led us to have 2 possible solutions. Because when I take the square root of a squared number, right, I get plus or minus 81. Okay? That kind of makes sense. Okay. So in this case, we have x times x. Oh, I don't know why it does that. Okay? Because x times x equals x squared, and 9 times 9 is equal 1, but negative 9 times negative 9 also equals 81. Okay, so this leads us to find the real roots of each of these equations. Okay, sorry, this is awesome. All of my I guess the order of my appearance and stuff is off. So if we look at 5 times x squared is equal to 15, right? We know that x squared is equal to 3, right? Because we divide both sides by 5. Then if I take the square root, I get plus or minus square root of 3. For this one, what would I do? Subtract 4, and I get x squared is equal to negative 4, which we have no real roots. So that was the key point for this question. Yes, we can find the imaginary roots, which would be plus or minus 2i, right? But when we're asking for just the real roots, we just want, we know that there's none, right? So we're going to have imaginary roots here. Okay? And then what about for something like this? Okay? I would subtract 16 from both sides, right? And then I would divide both sides by 25. Then I would take the square root of both sides, and then get plus or minus 1 over 5. Okay? And that's, again, when we're solving quadratics, again, when we're trying to solve it, that's a lot of reasons why we have 2 solutions, 2 possible solutions. Okay? So, here's some properties of radicals. Okay? And this has changed up a little bit from what might be taught in other classes and so on and so forth. So if I'm taking the square root, right, of a variable, and I'm just trying to simplify, if n is odd, so this is the 3rd root of n to the 3rd, for example, right? So 3rd root of b to the 3rd, for example, right? If b is odd, right, if I take essentially the square of that one, right, I'm going to get b, okay? Now, if b is even, an even value, if n is even, so I'm taking the square roots, right, I'm going to get whatever the absolute value is, okay, of b. Because in this case, if b is negative 2, right, we can't do the square root of negative 2, so it's a non-real solution, right? But if I square it, I still have to get a value out of here. In that case, that would be 2, okay? So essentially just making sure it's always positive for these kind of things, okay? So in this example, the square root of 7 squared would just be 7. Absolute value 7 is 7, so that just makes sense. But for odd, 3rd root of negative 5 cubed right, essentially gets rid of the radicals, right, and I'm just left with what's on the inside, which is -5. Yes? What do you mean? Yeah, so that's kind of what we're saying. So if I have the nth root and I take it to the nth power, all we've done is disintegrate it. That's why the squared goes away. And if I do x squared is equal to 4, take the square root of both sides, the squared goes away on the left side, right, but I still have plus or minus 4 on the right. Okay? That makes sense? So this is like, hopefully the absolute value thing will make sense a little bit later. It's mostly used for just simplifying, but when we're actually solving, you have the plus or minus that takes into effect. Okay? Okay? Sorry, I'm going to go back. Oh, no. Oh, crud. I don't know how to go back here. Oh, there we go. Okay? So if I'm taking, so now some things that you need to think about when we're taking the product or dividing radicals. So if I have the nth root of A and the nth root of B, and we're assuming that they're real values, so, I mean, but this actually technically kind of worked with imaginary either, right? But if I have the nth root of A times B, right, I can break it up into the nth root of A times the nth root of B, okay? And it works backwards the same way. If I have the nth root of A and I multiply it by the nth root of B, I can put them both under the same radical, right? So that's why these are equivalent statements, because it works both ways. Same thing if I have the nth root of A over B, right? I can just simplify it even more by saying, hey, let's take the nth root of A and divide it by the nth root of B, and that's still going to give me the exact same thing. Again, a lot of this stuff should be a bit of review. Okay? Okay. So some things to keep in mind. Okay? When we have an expression with nth roots, right, we consider it in its simplest form, right, when no radicand contains a factor other than one that is the perfect nth power. Basically what we're saying is we've taken out all the possible nth roots that we can. Okay? So if I still have an nth root in there, it's not simplified. For example, if I was taking like the third root of, let's just say, 168. No. Yeah, 168. Okay, if I took the third root of 168, right, that's 84 times 2. Well, I know the third root of 84. No, I should be, it's 128. There we go. Third root of 128. That's 64 times 2. I take the third root of 64, which I believe is 4. Okay? Factor that out. So I've got 4, third root of 2, and I can't get rid of that 2. So that would be in simplest form. Okay? The second is every denominator has been rationalized. Now, hopefully by this point you've seen rationalizing denominators. We've talked about it a little bit when we were dealing with imaginary numbers. Okay? So here's some, okay. And so this is the part that really kind of sucks, and I apologize. Those squares, those are actually meant to be multiplication symbols. Okay? I don't know why it came out squares, but they are supposed to be multiplication symbols. Okay? I apologize. All right? So in this example, all right, if I have square root of 98, I can break that up into the square root of 49 times 2, right? Which then breaks up into the square root of 49 times the square root of 2, right? And which will equal square root of 7 over 2. Now, or in this case, right, another way that you could think about it, right? Again, there's multiple ways that you can do this. Well, square root of 49 is 7, 7 rad 2. Or instead of going 49 times 2, I could have broken it up into all of its prime factors. And I could have taken that, well, this is the square root of 7 times 2, right? Well, that's got a perfect square in here. I can get rid of that, or I can pull those 2 out, and I've got 7 rad 2. Okay? For the second one, for number 2, I've got square root of 16 over 9, or square root of 16 over 9, right? And I can, and most of you go, okay, well, that's 4 over 3. But the reason that I can do that is because it's the same thing as taking the square root of 16 over the square root of 9, which we both know both of those values, which are 4 and 3. Okay? Does that make sense? Okay. Oh, sorry, that's the circle is meant to show that, hey, I found a pair, right? I've got 2, and I'm taking the second root, okay? See, this is what I mean why it gets a little bit more confusing. So, for number 3, if I take the third root of 25 and I multiply it by the third root of 10, okay? So again, this is working backwards. I can combine those, and I can go, well, this is the third root of 25 times 10, which, again, if I factor out the 25, I see this is 5 times 5 times 5 times 2, right? Because it's 5 times 5 times 2, which would give me 5, 3, or third root of 2. Okay, because I've got 3 sets here. Because again, my nth root, I'm looking for sets of 3 values that multiply together to give me that. Okay, that's why I can factor out that 5. Okay. So again, it kind of helps us with simplifying. Okay. So now if we assume that each radical represents a real number, this one's gonna be a bit tough for me to do because this is kind of chock full of errors here. And I'll explain that in just a second. All right, so I take the square root of 2a squared b, right? We don't know what a and b values actually are, okay? But I can break it up still, right? And because I see that we have a perfect square in there, which is a, right? So I can take and I can rearrange it. I can whatever the products are on the inside, I can rearrange it however I want to. And so now I've broken it up into square root of a squared times square root of 2b. Now, the issue with this one, okay, and I don't think it'll let me write on here, is what's the error with the solution number 6? Does anyone see it? What happens if a is a negative value? We wouldn't have any real solutions in there. We're missing i's and stuff. So for number 6, the actual solution has to be absolute value of a times the square root of 2b. Okay? Because in this case, n was even. Okay? So this needs to be the absolute value of a times the square root of 2b. Number 7 is going to have a similar situation. Okay? So if I take the square root of 36, w cubed, and I break that up and I got 36 times w squared times w, okay? Well, I know the square root of 36 is 6, and I know the square root of w squared is w. Well, absolute value w. So I can break it up into all its parts, and I can get that this is 6 absolute value of w times the square root of w. Okay. Do I have any questions so far? Sorry, I know I'm kind of going a little fast. Oops, sorry. Okay. Moving on, I hope. Right. So again, if for rationalizing denominators, okay, we're trying to rationalize denominators. So if I've got an example like number 9, where I take the square root of 5 over 3, and I try to simplify that, I get square root of 5 over square root of 3. That doesn't simplify anymore. However, it is an improper form. Okay, my denominator is not rationalized. So in order to rationalize it, right, all I do is multiply it, right, by essentially both the top and bottom by the denominator. Okay, and the reason why is the square root of 3 times the square root of 3 will be 3, because it's the same thing as the square root of 3 squared. Okay? But then I need to still multiply the top, and so I'm left with square root of 5 times 3, which would give me square root of 15 over 3. Yes? Okay, divide by, so look at the fingers on your hand. Divide it into square root of 2 parts. Right? I can divide it into 2 parts, right? Divide it into 3 parts, and divide it in all these different parts. But if I try to divide it into the square root of 2 parts, it's impossible. So we can't ever divide by a square root. Okay? Most of the time, you actually don't even divide by irrational numbers because it can't really happen. Okay? So that's kind of why it's not in proper form. No, I want to go back. This one's important. Okay? So now let's just say I have the 4 over third root of c. Okay? In order to rationalize that denominator, okay, I'd actually have to multiply it by third root of c squared. And the reason why, okay, is the third root of c, if I multiply it by just itself, third root of c, that'll just give me the third root of c squared. That doesn't actually rationalize my denominator at all. So I have to make it, right? I have to make the inside have the same power as the outside, essentially. Okay? So so if it's the third root, I need to make sure that I have 3 c's in there. Okay? Because when I get to this part right here, third root of c cubed, right? That's where c is going to be by itself, and that's when it's going to be rationalized. Okay? Now, will it make the top very complicated? Yeah, of course. Right? But it's still doable. Okay? Any questions so far? Okay, I think I have one more slide in here, but I don't like this one because it's actually this technically works. This doesn't work because there's no. We're not going to do this. Worry about this slide. Don't worry about it because it's wrong. Okay. So now what we're going to do is those worksheets that I had you pull up. First thing that we're going to do is I'm just going to, I've got all the solutions for you down at the bottom, right? So if you want to see them. But I kind of want to just kind of go through and address some things, okay? So how we might simplify this, okay? I'm going to do just a couple of problems here. If I look at number 1, right, and I multiply them together, square root of 6 times the square root of 6, this is the same thing as the square root of 6 squared. Okay? Well, what's the square root of 6 squared? It's 6. Now, we're not, we technically, right, we're supposed to do plus or minus 6, but we're only do that when we're solving. If we're simplifying, we are just looking for the principal root. Okay? Now, for example on actually these ones you can all do, but the ones that I really wanted to focus on was number 13. Okay? Number 13. Okay? If I go square root of 12 times x, or square root of 12x times the square root of 3x squared, all right, and I multiply those together, applying my properties, this is the same thing as the square root of 12 times 3 times x squared. Okay? Well, I already have 2 x's in here. Okay? So I don't need to combine those. But remember, when I'm taking the square root of x squared, right? If I'm taking out that x squared, what do I have to do? Now, let's hold on for that for just a second. Okay? Let's look at the rest of this. I have 12 times 3. What's 12 times 3? 36. Okay? And then I'm left with x times, and again, I'm going to leave this as x squared because I already have 2 x's. I don't want to combine them because there's just no point at this point. Okay? Now, when I simplify this, I know the square root of 36 is what? 6. So I have 6, and then I have the square root of x squared, which is what? Absolute value of x. Okay? Times x. Because that's all that was left inside. Okay? And again, unfortunately, and I want you to focus on that absolute value part, but unfortunately, your solutions in here don't necessarily have those. So for now, it's okay while we're practicing this. It's okay if you don't include it. When we start getting into solving and stuff, it'll become a lot more important. Okay? So just kind of keep that in mind. Okay, but we've done enough examples right now, so we can go ahead and I'll leave you guys. If you want to practice these, you can, and you have the solutions. Same, but for dividing, I also wanted to go through some examples as well. Okay. All right, so for number one, so again, for rationalizing the denominator, right, square root of 6, square root of 2, they both don't have an actual square root. So what can I do, right? Sorry. Ugh. Oh my goodness, this thing is so much harder to work. There we go. What can I do in order to rationalize the denominator here? Multiply the top and bottom by the square root of 2. Please keep in mind that we're not changing anything when we're doing this. We're really not, because what am I actually multiplying by? Multiplying by 1, right? Square root of 2 over square root of 2 is 1. So when I multiply straight across, and I get that this is the square root of 6 times 2 all over square root of 2 squared, which should equal plus or minus 2 technically, but again, we're thinking about the principal one, so it should just be 2. And then square root of 6 times 2 is just simply, what's that? Yes, it would. Okay. Because this is the same thing as, I think it'll work. Did you say 3 rad 2? 2 rad 3. Because it's the same thing as 3 times 2 times 2. And again, we notice, hey, I've got 2 2's here. So this is simplified to 2 rad 3 over 2, which just rad 3. Again, so when you're actually dividing these, right, a lot of times when you simplify them, you might simplify them all the way down and realize, hey, right, I've gotten rid of all of my denominators when I'm just by rationalizing the denominator. It really does help. Okay. All right, and then I think that was the only other one I wanted to look at. No, I wanted to look at number 6. Okay. Number 6, same kind of idea here. Okay. I want to multiply by the what? Right, but I can do some little tips and tricks first. Okay. First thing I'm going to do is I'm going to apply the other property. That this is the same thing as 16x to the 4th over 12x. And then I can simplify that. Okay? And so when I simplify the inside, I'm left with, well, 16 over 12 just becomes what? 4 over 3. And then I got rid of one of the x's in the denominator. So it's 4x cubed over square root of 3. Sorry, 4x cubed over 3. Now I can simplify that. Now I can turn this back into, so now this is 4x cubed over rad 3. And so instead of having to multiply by an x on the inside, right, I've gotten rid of the x in the denominator. Now it's a lot more easier problem for me to actually rationalize. So now all I do is multiply it by rad 3 over rad 3. And I get that this is square root of 4x cubed times 3 all over 3. Okay, which then becomes square root of 2 times 2. Oh, sorry. Let's go back. Let's simplify this first. Yeah, and that's kind of what we're doing here. Square root of 4 is what? 2. So this would be 2, and then I can pull out one set of x's. Okay. then now I can just multiply by rad 3 over rad 3. And so I'm left with 2 absolute value of x rad 3x all over 3. And I think the bottom for number 6 has 2x rad 3x over 3. Okay, I forgot the absolute value. Okay. But again, so part of why I did that, as long as I apply my rules, it doesn't matter when or where. As long as I apply them correctly, I can do whatever it takes to simplify this. Could I have just gone ahead and done this square root of 16 over 4 over 12, square root of 12x, and then rationalize the denominator? Yeah, absolutely. I could have done it any which order that I wanted to. Okay? And that's why I wanted to show you this problem, is there's more than one way to do it. So whichever way feels comfortable for you, whichever way makes more sense to you, do it that way. As long as you apply your rules properly, right? It's not going to matter. Okay? You're going to arrive at the same conclusion no matter what. Okay. Are there any questions on this? Okay. So I'm going to let you, so I'm going to stop the video.